In this video, we're going to talk about cyclic redundancy check, CRC. But before we talk about CRC, we need to know why do we want to use something like CRC. When a transmitter sends an information or data to the receiver, an error may occur, which will lead to a sort of 1-bit or more than 1-bit change. And that's why we have several types of error. The single bit error, only 1-bit change, and usually caused by white noise. The burst error, a contiguous sequence of p bits change and usually caused by impulse noise or by fading in a wireless. The higher your rate is, the higher the error you will get in a burst error. Here is an example for every type of errors. The single bit error, and we see only 1-bit change. For the multiple bit error, we have more than 1-bit change. And for the burst error, we have 5 contiguous bit change. Redundancy. Well, from its name, a redundancy is sort of an extra thing, so it's not a data, it's something that we use so that the receiver can know if there is an error or not on the data. So how we do that? Well, we have our data here, and then there is a generating function. We can think of it as a black box for now. Then it will provide us with a redundancy check. Then the transmitter will send this data beside this redundancy check. Then the receiver receives this frame, and it has a checking functions that will tell whether we accept the data or we reject it. We will accept it if it's correct, and we will reject it if there is an error. Or we may correct it if there is an error. Not necessarily we reject it. Cyclic redundancy check, CRC. It's one type of error detections. There are several types of error detection, but we will stick with CRC for now. The procedure is the following. We have divisor, pause, the transmitter and receiver agree on this divisor with length n+1 bits. Then we will add to the data an n-bit sequence of zeros. Finally, we get the remainder, which is the CRC with length n bits. The transmitter then sends this data beside the CRC. Now the receiver has a divisor, and it received the frame sent by the transmitter so that we can calculate the remainder. Now if the remainder is 0, we accept our data, and if the remainder is non-zero, we reject our data or we try to correct it. Now as you can see here, we have a division, but we deal with a sequence of bits, zeros and 1. So we're not going to make the long divisions that you learned in high school. Rather, we will do what's so-called division modulo 2. And before we do that, we need to understand what is the meaning of arithmetic modulo 2. Modulo 2 arithmetic. Suppose we are talking about the sequence of integers, 0, 1, 2, 3, and so on. And we want to talk about the modulo 2 arithmetic. In this case, we have only two numbers, 0 and 1. So 0 is going to be mapped to 0, and 1 will be mapped to 1, 2 will be mapped to 0, 3 will be mapped to 1, and so on. So now we can say that A is equal to x modulo 2, or A equal to x in Z2, where Z2 is a ring modulo 2. So I can say 4 is equal to 2 modulo 2, 3 is equal to 1 modulo 2, and in general A is equal to the remainder of x and 2. Now usually binary are interesting, and this is show up here again, because A plus B modulo 2 is equal to A minus B modulo 2 is equal to A XOR P. If you picked any two numbers and you add them and then subtract them in modulo 2, then you're going to get the same result. And what is even more interesting, this result is equal to A XOR P. A quick review for XOR. XOR acts as a comparator that will provide you with 1 if and only if inputs are different and 0 otherwise. So now we are ready to apply our procedure. Let us assume the data is equal to x is equal to 1011, and the divisor is equal to d is equal to 1001 is equal to x cubed plus 1. This is another representation for the divisor. So according to the procedure, we have our data here, and we will add to it 3 zeros. Because n here is equal to 3, because the length of the divisor is equal to n plus 1 is equal to 4, so n is equal to 3 here. And here is our divisor, 1001, and then we will start to make our division. And 1 times 1001 will give us 1001. Now we will subtract, but remember the subtraction is the same as the addition is the same as the XOR. So usually we'll apply XOR directly. So 1, 1 will give us 0, and 1 and 0 will give us 1, 0 and 0 will give us 0, 1 and 1 will give us 0 again. So we only have these two. Then we will take a 0 from above, but we only have a 3 bits here, so we need another 0. So we will get this 0 too. But we will add 0 here since we got another 0. And then we multiply by 1, since 1 times 1001 is equal to 1001. And you may say 100 is less than the divisor 1001, and this is true in the long division, but here it's okay to do so as long as we have 4 bits. So if we have 4 bits, it's okay. We don't care if this number is smaller than the divisor or not. So again, we will make now our XOR here. 1 and 1 will give us 0, 0 and 0 will give us 0, and 0 and 0 will give us 0, 0 and 1 will give us 1, and then we will get 0 from above. And now those 3 bits are our CRC, which indeed was expected since we have the divisor with length 4, so the CRC with length 3. So now the transmitter is ready to send the frame, and this frame is consists of the data here and the CRC besides the data. So by this we apply the procedure of the transmitter. Now let us assume the receiver receives the data correctly and no error occurred. And of course we have the same divisor that we agree with the transmitter, so it is the time to apply the RX procedure, which is to divide the received frame by the divisor. Again, we will do the same what we did at the transmitter, and we will pick 1 times 1001 is equal to 1001, then we will make the XOR, will give us 0 here and 0 here, and 1 0 will give us 1, and 1 and 1 give us 0. Then we will take 0 from above, but since there are only 3 bits, then we are ready to take another 1, but we should put a 0 here, and then we put another 1 to multiply by 1001, and we will get 1001. Again, make an XOR, we will get 0 and 0 and 0 and 0, and we will take that 0 from above. Finally, we multiply by 0 to finish the process, which will give us again 0 0 0, and when you make an XOR, will give us with 0 0 0. Now since the output here is 0 0 0, that indicates that there is no error and the data is received correctly. On the other hand, if there was an error and a bit it changed, then when we do the RX procedure, we will get different answer than 0 0 0. Now you may wonder why this works. Now let us assume that this number is equal to A, and the CRC equal to the remainder, and the 1001 is equal to the divisor D. Now according to what we did here, we have A is equal to Q times D plus R, but then the receiver should receive this number here, which is A minus R. If you think about it, here was 3 zeros for A, and if we subtract 0 1 0 from A, which is the remainder, will give us this number. In fact, if we even did A plus R, we will again get this number. But from the previous equation, we have A minus R is equal to Q times D. So now, when we are at the receiver and apply that A minus R and divide it by D, well, this is exactly will equal to Q times D. So hence, the remainder here must equal to 0. And this is actually what happened here in this example. So this is sort of the intuition of why CRC works. Just keep in mind that these operations are done in Modulus arithmetic. We said before that the transmitter and receiver must agree on a specific divisor. Turns out that there is another way to express this divisor, which is in the form of polynomial. So this divisor actually that we can see here of 101001111 can be expressed as x to the 7 plus x to the 5 plus x squared plus x plus 1. You may wonder why we want to express the divisor in the form of polynomial. Well, what we did here actually called the channel coding, and there are whole courses, theory and textbooks on channel coding in which they make use of that polynomial representation. If you're interested in channel coding, you can enroll in a coding theory course, which may or may not be a grad topic depending on your department. Finally, the standard polynomials, CRC 12, CRC 16, CRC ITU, and CRC 32. Our time is up. Thank you for watching.